In this section, we're going to talk about how to work with expressions that involve rational exponents. So let's think about first what that actually means. We know what rational numbers are. Those are any numbers that can be expressed as a ratio. So that means that a rational exponent then is any exponent that can be expressed as a ratio. So this means that instead of just dealing with whole number exponents, which is what we're used to, say something like an exponent x squared, x cubed, x to the fourth, that's what we've been dealing with at this point. Now we're going to introduce the idea of a rational exponent, so any rational fraction that you can think of. So you could have x to the 1/2 power now, or x to the 5/2 power, or x to the 3/7 power, something like that. It turns out that these rational exponent expressions are related to the radical expressions that we've been working with so far in this chapter. There are a couple of statements in your book, I'm just going to repeat them right here, that relate rational exponents to these radical expressions. And the first rule is that if you have some number raised to the 1/n power, again 1/n would be a rational number, so that's why it's in this section, a to the 1/n is the same thing as taking the nth root of a. So for instance, got a couple of examples. If we're raising x to the 1/2 power, that's the same thing as taking the square root of x, because n in this case is 2. If we are raising y to the 1/5 power, that is the same thing as taking the 5th root of y. So that will be one important relationship to keep in mind. Something else that you want to keep in mind, another rule that we have, is that if you are taking both a root and raising an expression to some power, then it actually doesn't matter what order you do it in. So what I mean is, if you're taking the nth root of some number a to the m power, that's actually going to be equivalent to taking the nth root of a and then raising all of that to the mth power. So let's just make sure you understand what's happening here. And on the left side of this equation, what we're doing first is we are raising we're raising a to the mth power, and then we are taking the nth root. So we're doing the exponent first and the root second. On the right side of the equation, we're doing the opposite. We're taking the root first and then raising it to the nth power. But all this is saying is that it doesn't matter what order you do this in. So let's just convince ourselves that that is true. Let's see. Let's take, let's just do a general example. Let's say that we want to take the square root of x to the 4th. So this is an expression that we've been familiar with simplifying. We know that if the index is 2, this is an example, if the index is 2, then all we need to do is divide that exponent of 4 by 2, and we know that that is equal to x squared. So we know our expressions should simplify to x squared. Now this rule that we just talked about says that instead of raising x to the 4th power and then taking the square root, what we could do is take the square root of x and raise it to the 4th power. And it turns out that that is also equal to x squared, which is why the two expressions are equivalent to one another. So we can use those two relationships that we just talked about to rewrite various expressions. So for example, let's do this first situation. It says, what is x to the 3/4 in radical form? So right now we have an expression that has a rational exponent, and instead of using that rational exponent, we want to convert this into an expression with a radical. So what you're going to do is you're going to take a look, and whatever the denominator of your fraction is, that is going to become the index of your radical. So because our denominator is a 4, our index, this is going to be a 4th root. And then whatever your base is and whatever the numerator is, that's just what goes underneath the radical sign. So x to the 3/4 power is the same thing as the 4th root of x cubed. Now you can also go in the other direction, and that's what we'll do in just a second. All right, let's say in this case we want to convert the 6th root of x to the 9th into exponential form. So on the last slide we went from exponential form to radical form. Here we are going from radical form to exponential form. So we're just going in the opposite direction. In this case, whatever is underneath the radical sign, that's just going to be the base in your exponential expression. And then if it's being raised to a power, that'll be the numerator in your rational exponent. And then if whatever the index is, that will be the denominator for your rational exponent. So this is going to become x to the 9/6 power. And then of course, because we can simplify that fraction, this is equivalent to x to the 3/2 power. Which also means that if we convert it back, and this isn't what the question asked, we're going a little bit farther, if we converted this back into radical form, that would mean that the 6th root of x to the 9th is the same thing as the square root of x cubed. Because remember before we said whatever your denominator in that rational exponent is, that becomes the index in your root, and then your base, and then the numerator of the exponent is what goes underneath the radical. That becomes your radicand. Something that you will need to refresh your memory on in this section are the properties of rational exponents. These are things that you should already be familiar with, but you may be a little rusty on. The first one is that anytime you are multiplying two exponential expressions together that have the same base, you can simplify that by adding the two exponents together. So a to the mth power times a to the nth power is equivalent to a to the m plus nth power. I'll just do a quick example. So that means that x squared times x cubed is the same thing as x to the 5th. The second property of rational exponents that you need to recall is that if you raise a power to a power, so for instance if you have a to the mth power and you raise that expression to the nth power, that is the same thing as raising a to the m times nth power. So let's go back and do another example. So let's say this time we're taking x squared and we're raising that to the 3rd power. That means we have x squared showing up 3 times. So that gives us a total of x to the 6th, because you do 2 times 3 in that situation. One last property that you need to be familiar with is that if you have two factors inside of a set of parentheses and you're raising both factors to some exponent, we'll do ab to the mth power here, the product ab to the nth power, then it's a little bit like, it's the same idea sort of as distribution. You have to distribute, or you have to apply that exponent to both of the factors inside the parentheses. So that means this has to be a to the mth power times b to the mth power. So let's do one more example. Let's say that we are doing, we've got xy and we're squaring it. So that means that's equivalent to x squared, y squared. One last thing that you need to recall in regard to exponents is how to deal with a negative exponent in an expression. So for instance, if you have an expression, let's say x, let's just keep it simple to begin with and do x to the negative first power. What this means is that it's equivalent to 1 over x. What you can think of is that that negative exponent, to make it positive, what you have to do is move your x down to the denominator of the fraction, and then you can make the exponent positive. You could think of the same thing if for some reason you were presented with an expression of 1 over, let's say, y, y, that's better, y to the negative 3. That would be an awkward expression to deal with. If instead we wanted that exponent to be positive, we could then bring the y up to the numerator and make the exponent positive, so this would be equivalent to the expression y cubed. So you just need to keep in mind that moving or having a negative exponent means moving things from the numerator to the denominator or vice versa. There are lots of good examples in your textbook for this section, and I would strongly encourage you to read through those examples. But I want to work through one example right now that combines a lot of the ideas that I've presented in this video. So let's say we want to simplify this expression 8x to the 15th to the negative 1/3 power. Now if you want to go about simplifying this, there are different methods or different steps that you could take, or a different order of steps. There's not necessarily just one way to simplify an expression like this. So keep that in mind. Just because I'm doing it in a certain order doesn't mean you have to necessarily do things in the same order. What I'm going to deal with first is this negative exponent, because I find that kind of ugly. So instead of having, actually I take that back, I'm going to deal with this denominator of 3 in the exponent first. We know that if we have a rational exponent, whatever the denominator is can become the index on a radical expression. So that means if our denominator is 3, that means we're dealing with a cube root. And we are dealing with the cube root of 8x to the 15th raised to the negative first power. That seems like the best first step to me. Okay, so we definitely have a cube root. Now what I want to do is I want to simplify what we have in underneath the radical sign. I want to deal with the radicand now. And now I'm going to take care of this pesky negative exponent here, because that seems a little silly. So we also talked about the fact that if we have a negative exponent, then we can make that positive by moving the term that's being raised to the negative exponent to either the numerator or the denominator. So because right now 8x to the 15th is in the numerator, if I want to make that a positive exponent, I'm going to have to raise or move it to the denominator. So it's going to become 1 over 8x to the 15th. Now I don't need to write that we are raising this to the first power because that's just understood. But if I was dealing with something other than the first power, of course I would need to express that. Now we need to think about whether or not we can simplify what we have left. And of course we can. So here I'm going to take a step where I'm sort of doing something that is the opposite of what we've done in earlier sections. I'm actually going to split this fraction up to be the cube root of 1 over the cube root of 8x to the 15th. Now there's a reason I've done that, and it's because I've recognized that both 8 and x to the 15th are perfect cubes. So I'll be able to rationalize that denominator and get rid of that radical. Well, first of all, let's look at the cube root of 1, which is, of course, just 1. So that makes our numerator a little bit nicer to look at. Now let's look at the cube root of 8x to the 15th. I'm going to deal with the 8 first. So let's think, is 8 a perfect cube? And oh, luckily it is. And we should know at this point the cube root of 8 is 2. So that's nice. And then we need to deal with the x to the 15th component. And hopefully at this point you know that all you need to do here is take that 15th, the exponent of 15, and divide it by our index of 3, and we're going to get 2 times x to the 5th power. And there is your simplified version of our original expression.